this far. Okay, you can introduce Anna anytime.
Oh, sorry, let me also start my screen.
Okay. All right. Well, welcome everybody. Thank you for joining us. Happy to introduce our colloquium speaker for today for our second to our penultimate colloquium of the year. Today we have Anna Rosen as our colloquium speaker. Anna was an undergraduate. She got her BA from UC Berkeley, and then moved across the Bay Area to UC Santa Cruz, where she did a PhD with Enrico Ramirez Ruiz and Mark Krumholtz, which she completed in 2017, and then decided to flip coasts and go to the Harvard ITC, where she's an Einstein and ITC fellow at the CFA for the last few years. And she's a theorist working on a number of problems in star formation, as the title indicates, with a particular interest in massive stars, but has worked on a range of topics, including decades-old problems of how you actually make a 10 solar mass star, through how those stars influence the medium around them through winds, radiation, hydrodynamics, astrophysical turbulence, and their sort of interactions with the ISM. As I said, has worked on a number of things we'll hopefully hear about. If you Google around, you might see her on some recent simulation papers and pretty pictures that I've been lucky enough to collaborate with her on, and I look forward to hearing more. So thank you, Anna. Take it away.
Thank you. Yeah, thank you for the introduction. Yeah, it's really exciting to be at Caltech. Unfortunately, it would have been nice to do this in person, since I'm actually from Los Angeles, from the San Fernando Valley. So I apologize in advance for my Valley Girl accent. But as Phil mentioned, my research is focused on studying stellar feedback in the context of star formation. And as many of you know, especially highlighting Phil's work, stellar feedback, and that's the injection of energy and momentum by young stars into the interstellar medium, is one of the biggest uncertainties in both star and galaxy formation. And that's just because during their formation, as these stars grow in mass, they give off a lot of light and winds and outflows and so on that can have a huge impact on their natal environment. And so this is my favorite example. This is 30 Doradus and the Large Magellanic Cloud. And this is showing a composite image showing basically how impactful stellar feedback can be on the surrounding gas that should, you would hope that should, just due to gravity alone, should collapse to form stars. But as the gas is collapsing and forming stars, those stars will heat up the surrounding gas. And so, for example, this multi-composite image shows the cool gas illuminated by young stars. So that's like the first absorption of the stellar radiation from the stars themselves. And you can see that here, and you can see this pretty dominant around this central massive star cluster here. This is R136, which is our closest analog to a superstar cluster in our local universe. Likewise, the surrounding dust will absorb that radiation, and that will heat up the dust, and you get this dust for process radiation, which we see in the infrared, which you can see in the red here, and that has a much larger impact of the radiation from stars throughout the molecular cloud out of which these stars formed from. And then finally, because 30 Doradus has so many massive stars, these stars are so bright that they are able to launch fast winds from their surface. And these winds leave at the escape speed or higher, that's 1,000 kilometers per second or more. And as they collide with the surrounding gas, they shock heat to millions of degrees Kelvin and then expand. And we can see that with Chandra in the blue here. And that hot gas pressure will expand and envelope and push on the surrounding cool gas. leaving these vacancies that we can see here. The collective effort of all of these processes is to make star formation inefficient in both molecular clouds and the overall galaxies. So, like I just showed with the Doradus, you can see that feedback has a huge impact on the surrounding molecular gas and galaxies. And feedback is dominated by massive stars. However, if you look at the IMF, so the initial mass function, this is showing for a given, let's say, fully sampled stellar population, what fraction of stars you expect to be like 10 solar masses and above. And it turns out that from the Karupa IMF and similar IMFs that have been measured in stellar populations, you find that only about 1% of stars are massive. But then if you look at the energy output from those stars, so let's say just looking at the stellar radiation from this given stellar population, you find that 97% of the stellar radiation comes from the massive stars alone. And so it's really the massive stars and star-forming galaxies that dominate the energy output. And so I like to think that massive stars are the 1% of the universe. And like I mentioned before, so that picture of the Doradus is very messy. It's a whole bunch of processes happening at once that is impacting the surrounding gas. And so on the individual scale, stars feedback on their environments in a variety of ways. The first is through radiation pressure. And there's 3 components to this. The first is the first absorption of the stellar radiation. And so that's high energy radiation, the absorption from dust. And likewise, that dust will heat up and reprocess the radiation, and you get this addition to the radiation pressure in star-forming environments. So that's dust reprocessed radiation. And then likewise, you also, since these stars are so hot, they give off a lot of ionizing radiation. So you can photo-ionize the nearby gas, launching H2 regions. And then as these stars become so massive and bright, their temperatures are really high, and then they can launch these radiatively driven winds from their surface. And so these are spherical winds that have to leave at above the escape speed of the star. They'll leave the star at thousands of kilometers per second. And that wind will collide with the surrounding ISM and also with the winds of nearby stars, leading to this really hot gas that we can observe with X-ray telescopes like Chandra. Also, while these stars are actively accreting, they launch protostellar outflows. So as these stars accrete from an accretion disk, they'll launch jets, and those jets can actually entrain molecular material and blow material out, leading to low star formation efficiencies in molecular cores. And then finally, at the end of their lives, massive stars explode in supernovae explosions, and this can impact a lot of energy and momentum to the surrounding ISM and eject a lot of gas. On larger scales, so in a collection of stars, so star clusters, like I mentioned before, the collective effort or the collective, the collective effort of these feedback processes or the integrated effect of these feedback processes can actually eject gas from surrounding, from the natal environment. So it can actually, once you build up a star cluster, you can actually have enough momentum and energy deposited into the surrounding gas that you can actually eject material. And so this is NGC 3603, which is a massive star cluster in our galaxy. And you can see with the collection of stars here that the integrated effect of feedback has actually ejected the rest of the natal material. And so this can shut off star formation in molecular clouds. And so, for example, one of the reasons why you don't see all the gas being converted into stars is because as these stars are actively forming, they will push on the surrounding gas and make star formation inefficient. And so the star formation efficiency that we observe in molecular clouds is about 1% to 10%. So this is a reason why we see inefficient star formation on the GMC scale, which then impacts, of course, galaxies. And with galaxies, the integrated effect of feedback can actually launch winds. And so here, this is shown M82, and you see these nice galactic outflows from the galaxy itself. The red here shows the infrared emission. So this is cold, dusty gas that's being ejected. And if we look again with multi-wavelength observations, we can see it's this hot material that's expanding away. This material is due to stellar winds and supernovae that's ejecting this gas out of the galaxy, leading to low star formation efficiencies in galaxies themselves. Now, obviously, stellar feedback is an all-encompassing area that impacts the formation of individual stars all the way to galaxy evolution. And so this topic has really gotten very popular over the last several decades. So here is just an example of, I just looked through ADS to find all the abstracts that include stellar feedback. And this is not even including the individual processes. So this number is probably a lot more. So I like to think that stellar feedback is all the rage nowadays because it has an impact on so many different areas of astrophysics. And we know that it's massive stars that are directly related to the overall injection of energy and momentum into these galaxies. And so it's really important for us to understand how massive stars form and how does stellar feedback shut off their formation. So the first question is, well, how do massive stars form? Do they form like low mass stars, or is it a more complicated, more dynamical picture? So here, there's two competing main theories over the years. The first is core accretion, and the core accretion model is kind of like a ramp up of low mass star formation in which you have these massive cores, which is the equivalent to low mass gas pressure supported cores. But now these cores are much more massive and they're supported by either turbulence or magnetic fields. And we're, now with observations from ALMA and other radio telescopes, we do see these massive clumps. And these may be the precursors to massive stars. And so massive stars tend to form in the densest environments and what are known as IRDC, so infrared dark clouds. These clouds will then are supported, contain turbulence, and also they're magnetic, or they have magnetic fields. And so these clumps will then collapse or fragment into smaller clumps or cores. And then these might be the precursors to massive stars. The requirements for this theory is the existence of virilae. So these are dense cores that are supported by either magnetic pressure or gas pressure, or turbulent pressure. However, one of the problems with this theory is that observations of these cores from all different scales find that the turbulence is not strong enough to support them. And instead, they may be supported by magnetic fields. And so now observations looking at the magnetic field topology and magnetic field strengths from observatories like ALMA and others are looking at that now to kind of see, do these massive cores, are they stable to collapse? And then they can become unstable to form a massive star. The other theory is competitive accretion. And this is that the massive stars form from the collapse of Jeans mass cores. So these are protostellar cores that are, or starless cores that are about solar mass or so on, that are supported by gas pressure. And then because of the mass flow within this cluster, the mass flow is going to fall down the cluster potential. And it's the massive stars at the bottom of the cluster potential that kind of steals mass from nearby accreting low mass stars. And so we do see these dynamical signatures in these dense infrared dark clouds. So for example, SDC 13, you see these filamentary structures where you do have this large scale accretion flow along filaments that are feeding massive stars. And for example, too, we do also observe this. This is an example of another massive star forming region with a few massive protostars that are, so these three stars here are plotted here on the HR diagram. They have very high luminosities and large molecular outflows. So these are jets that are entraining molecular material as these stars are forming. And you do see this dynamical accretion onto these large scales. So the truth is that massive star formation is probably a combination of these two theories, where you do get these clumps that are larger, or cores that are larger than Jeans mass cores, but you have a more dynamical process of feeding material to the stars themselves as they are actively forming. And so we like to think of, massive star formation as a multi-scale, multi-physics problem. It really relies on all these different physics, the magnetic fields, turbulence, gravity, and also stellar feedback. And all those things will impact accretion onto the stars themselves. So just to go through my talk, I like to look at the role of stellar feedback and massive star formation on a piece by piece to get a better understanding of how these different feedback processes affect accretion and also work together to see how massive stars can grow and what may ultimately shut off accretion onto stars, setting the maximum stellar mass. So first, I'm going to talk about the role that radiation pressure plays. And this is, as Bill said, this is an age-old problem that's been given a lot of attention for decades. And this started back in the 1970s with a simple thought experiment. If you have a cloud of material and it collapses, and then that star continues to grow in mass, can you have radiation actually shut off the accretion flow? So as the star gets more and more massive, its luminosity grows quite quickly. And because both the fall due to gravity, or the force due to gravity and the force due to radiation, you have this 1/r² dependence. If the luminosity is large enough, then you can actually overturn the accretion flow. And so here I'm showing for the radiative force that you have this 1 + F trap factor. And this takes into account the first absorption of the radiation field, and then also the subsequent re-emissions, or the boost in the radiation pressure due to the fact that the radiation field is reprocessed by the dust. And so this adds on to the so this F trap factor is really important in kind of setting how efficient radiation pressure is during the star formation process. And so, oh yeah.
Can you enumerate what exactly is the coupling of the photons? How is the pressure conveyed? And I know it's not electron scattering here.
Oh, actually, I will show that in my next slide. So it's so in this context. Oh yeah, well, so dust is the primary absorber for the radiation field from stars, especially for the high frequency radiation. The opacity is very high. And so because these regions are very opaque, you can get multiple absorptions from the dust and the surrounding gas. Okay. So many of us use this trapping. This F trap is known as this trapping factor, about how these multiple absorptions and reemissions actually enhance the radiation field. Did that answer your question?
Yeah, thanks.
Okay, you're welcome. Okay, so back in the day, back in the 70s, when people were studying this, it was believed that, assuming isotropic accretion, that you would actually halt the accretion flow into the star when the star reaches about 20 solar masses. And this was known as the radiation pressure barrier. But obviously, we know that we have observed stars more massive than this. We've seen supernovae from progenitors that are more massive than this. And so there are more, so 20 solar masses is not the cutoff for stellar masses. And so there has to be another way for this material to fall down towards the star. And so really what you need instead of an isotropic accretion flow is an anisotropic accretion flow. And I'll talk more in detail, and I'll talk more about that in a little bit. Oh yeah, so like I said, we know that there's stars much more massive. So going back to 3D Doradus, I'll go back to this star cluster a lot, or this H2 region a lot. The study by Schneider et al., they did by looking at the stars, they estimated what the initial mass function of 3D Dora is, and they actually find a top-heavy IMF where stars were as big as 200 solar masses. And so the question is, does feedback set the maximum stellar mass? And obviously, that picture of isotropic accretion is incomplete because the initial masses that we're seeing for stars and star clusters like 3D Doradus is much higher. Now, the problem is actually observing massive star formation. So being able to zoom in and see this up close. And that's just because massive star formation, at least within our galaxy, occurs very far away, so kiloparsecs away. And even though the sources are very bright, they're highly obscured. They form in the densest regions in our galaxy. And so it's really kind of hard to get a close up. And so also the formation timescale is really short because they contract the main sequence very quickly. And so to see a glimpse of their formation, you have to catch it in the act, which is not always so easy. And so we can turn to numerical simulations to get a better insight of how, the physics behind massive star formation and how feedback actually affects the accretion onto massive stars so that they can continue to grow, or how feedback can actually shut off accretion. So like I mentioned before, so with the radiation pressure, there's two components. There's the first absorption, and there's also this trapping factor due to the reprocessing by interstellar dust. And so to answer your previous question, so this is showing the dust opacity. The dust opacity increases by orders of magnitude for higher frequency radiation. And since these stars get so hot and bright, you have a lot of high frequency radiation that can actually drive radiation pressure driven bubbles, or can actually blow material away as the stars are forming. And so we developed this new hybrid radiation technique, which treats the stars and then the interstellar gas differently. So for the stars, we use adaptive ray tracing for the point sources. So we treat the stars as point sources, and we use adaptive ray tracing, and we were able to solve the radiative transfer equation exactly, and be able to properly deposit the energy momentum as the radiation goes through the gas. And then likewise, the surrounding gas and dust, or the surrounding dust, will absorb that radiation and then re-emit. And so we use a moment method, which is an approximation to the radiative transfer method that is commonly used in studying radiative processes and numerical or astrophysical simulations, just because it would be prohibitively expensive to actually solve it exactly for the whole domain. And so with this, we can do a better treatment of the radiation field from stars and properly treat the absorption of the momentum from the stars themselves. So this module was added to the Orion AMR adaptive mesh refinement simulation code, which is a Cartesian-based simulation code, and adaptively refines in areas of interest, so such as high densities, or density gradients and other things. We solved the radiation hydrodynamic equations with Orion, which basically just describes conservation of mass, momentum, energy, and radiation energy. We also include star particles. So these are Lagrangian sync particles that can accrete material, nearby material, and that affects the dynamics of these stars, excuse me, and the growth of these stars. And then we solve the Poisson equation to update gravity. So I'll show you an example from a simulation that we ran. So this is showing the collapse of 150 solar mass core, this core, the top panel shows the whole. The top panel show the whole core collapsing, and the bottom panels are a zoom in. And these are two different perspectives. And we see the core turbulent, since we know that stars form in turbulent environments. And as the star forms, it gets more and more massive. We see that the radiation pressure blow these bubbles out of the way. So you get these radiation pressure dominated bubbles that can blow material away. But you also develop an accretion dust that is very dense and becomes shielded by the radiation field. So you can still accrete material that way. And so what we ultimately find is that the radiation pressure is no longer a barrier, and that there's a variety of ways you can actually accrete material onto the star. So the first is it happens early on, and that's through the accretion of these filaments that are set by turbulence. So as the core is collapsing, these filaments become optically thick and fall down towards the star. Likewise, as these radiative pressure bubbles start to expand, they actually become unstable, become radiative. They become really Taylor unstable, and that's just because you have this low density radiation pressure dominated fluid or low density fluid that is actually pushing on the bubble shells as the bubbles are expanding, and that can develop these really Taylor fingers that we see here that can penetrate through the bubble and potentially bring more material to the star. And then finally, we also get these very dense, optically thick accretion disks that supply most of the material. So the main point is that as long as you have an accretion flow, that can overcome the ram pressure, the accretion flow can overcome that of radiation. So here it's just showing the mass weighted. So just looking at the material that's falling in instead of the spherically average, you find that the star can continue to grow. So radiation pressure is likely not responsible for setting the maximum mass of massive stars. So another thing I had mentioned earlier is that, like I said, these cores are turbulent in the virial states. So that depends on the amount of like the velocity dispersion of the core. So a higher velocity dispersion will slow down the collapse. What we find, so this was just comparing two simulations, like I showed the first one that I showed before, and then a similar simulation with the higher velocity dispersion. So this is a virialized core. And what we find is that if you have a subvirial core, so there's no support, it just instantly collapses. You get a higher accretion rate onto the star, so you grow the star a lot faster. And then eventually the accretion rate is pretty much dictated by the accretion disk that forms at the end. However, when you include with when you start with the higher velocity dispersion, you do get more turbulent fragmentation. And so you can end up with more wide companions. So the initial states, the initial turbulent state of the gas out of which these stars form is very important for multiplicity of massive stars and the formation of wide companions. So what about protostellar outflows? Well, we know that protostellar outflows are ubiquitous for both low mass and high mass star formation, and that's just because, as we showed before, there's an accretion disk that brings material to the star. And due to the magnetic processes, accretion of material and conservation of angular momentum, you're going to have these magnetically launched jets that escape from the star. And since these stars are forming in highly emitted environments, as those jets move away from the star, they're going to entrain material that can eventually be ejected from the star forming environment or from the core itself. Additionally, too, the actually more important than momentum from radiation. So for example, this is showing a sample of the momentum measured from a series of outflows from high mass star forming environments or high mass star forming cores. And I overplotted a line here with the radiation momentum, which is just L over C. And you can see that the momentum in the outflows is larger. And so these powerful jets can actually drive these wide angle molecular outflows from star forming cores and potentially eject the material, leading to low star formation efficiencies. So if we compare, so here's a similar simulation with only radiation, and then a similar simulation, everything's the same, except now we have turned on outflows. We use a subgrid model where a fraction of the accreted mass goes into the outflow itself. And what we find is that the outflows have a larger effect on the star forming on the core, and you can actually eject material. Whereas when you only have radiation pressure, you develop these radiation pressure driven bubbles. The star grows a lot faster because you're not losing mass to the jet, but these radiation pressure driven bubbles expand, become unstable, and start to collapse. Whereas the outflows are more efficient at evacuating material along the bipolar directions of the star. Additionally, once you get this outbreak from the outflows, you can actually reduce radiative heating because you can allow radiation to escape. And so this has important impacts for actually setting the star formation efficiency of star forming cores, because you can outflows are more effective at ejecting the material. But of course, everyone always asks, what about magnetic fields? And so we know that the ISM is magnetized, and dense gas tends to be what's known as supercritical. So this mu phi factor here is just the ratio of gravity to magnetic pressure. And the high density gas out of which stars form tend to be supercritical, meaning that gravity is a little bit stronger. And so the effect of magnetic pressure should be that it should slow down the collapse and also reduce fragmentation. which is what we see when we include magnetic fields. So here I'm comparing a similar simulation, but now we include magnetic fields. We have a massive flux of 2, consistent with observations of massive pores. And we see that the accretion rate is generally smaller. And so the star itself grows, the collapse slows down, and so the star has a lower accretion rate. Additionally, it affects the formation of accretion just around the star, because as material is falling down towards the star, normally, if they're in the absence of magnetic fields, that material, because it has angular momentum, will circularize near the star, and the location where it circularizes depends on the angular momentum content. However, when you do have magnetic fields, you actually remove angular momentum from the infalling material, and that can lead to smaller disks. And also reduces fragmentation. So for example, we get a smaller disk here and we have no fragmentation. We don't have any turbulent fragmentation, no disk fragmentation like we do here when we don't include magnetic fields. And so I just want to warn that these simulations do not include non-ideal effects. So with ideal MHD, you have flux freezing, which means that the magnetic field can be amplified because you're dragging the field lines with you as you collapse. But when you have non-ideal magnetic effects, that it can actually reduce flux freezing. And so that can have an impact where you might see more fragmentation or a larger accretion disk towards the end. And then finally, too, so the impact of radiation pressure and outflows is to, especially with radiation, is to drive these radiation pressure dominated bubbles that can then expand. And when we include magnetic fields, we find that these bubbles are actually a lot smaller. And so what we're finding is that as the material collapses, as these bubbles are expanding, so the material is collapsing, you drive these radiation pressure driven bubbles. And as they expand, they're going to drive these low density bubbles, and then magnetic flux is going to be swept up in the shells, and actually the magnetic tension associated with the amplifying of the magnetic field is actually going to confine these bubbles. So the influence of magnetic fields actually reduces the effect of radiation pressure and makes these radiation pressure driven bubbles a lot smaller. And then also the effect of magnetic fields also changes the structure of the entrained outflows that we see. So for example, the top panels here show 2 snapshots for the entrained outflows from massive star, and then also the low mass companions that form because we get more fragmentation. But you do see the outflows are a bit messy, and that's just because as a star is accreting material from all different directions, it can process. And so you get these messy collimated outflows, which is looks similar to what we're seeing in observations, like I showed in one of the previous plots from Adam Avison. But when you include magnetic fields, you actually get this magnetic levitation effect. The first thing is that it's easier to kind of push this material out because the core itself is not collapsing as fast. And then also this levitation effect leads to this larger collimation angle. So you get wider outflows depending on how magnetized the surrounding material is, which I'm quantifying here. And this is showing the volume fraction as a function of stellar mass for the stars. And you can see once outflows become very powerful at about 20 solar masses, the volume covering fraction for the outflows in the magnetic case becomes a lot larger. And then we can also look at the mass, momentum, and energy budget. So the idea here is based on what I inject, so the mass, momentum, and energy that I eject, how much are we getting out in those entrained outflows? How much is actually transferred to the surrounding gas? So in agreement with observations, we're finding about a 3-to-1 ratio for the entrained mass to the launch mass. And this is what's typically observed for low mass star forming cores. Outflows in the case of low mass star formation is the feedback mechanism that we believe actually sets the low star formation efficiencies of cores, and the fact that the core mass function and the IMF is off by a factor of 2/3. However, if you look at the injected, the entrained momentum divided by the injected momentum and energy, what we find is only about 25% of the entrained momentum is actually in the outflow. So all that you put in is not what you get out. And so that's just because you can lose some of this momentum and energy due to radiative losses. And so likewise, we only see about 5%. So the entrained outflow momentum and kinetic energy is about 25 and 5% of the injected quantities. So this basically says that all the energy momentum that you're putting in with outflows is not exactly what you're getting out. You're losing some of that. And then likewise, we find that in order to get the observed star formation efficiencies, so this is showing the basically the stellar mass divided by the initial core mass. The 33% here is what is from observations of low mass star formation. And then the 40% here is for what's observed from high mass star formation. And what we find is that radiation alone cannot be responsible for the low star formation efficiencies that we see, and that we require outflows to actually set the star formation efficiencies of massive cores. And then likewise, this is always exciting as a theorist, is when your results match the observations. And so this is showing the outflow force and the entrained outflows for both simulations. So this outflow force doesn't change much based on the whether you have magnetic fields or not, as a function of the source luminosity. And then overplotted are the results from Mott et al., who looked at the outflows from a large sample of massive protostars, and we see that our results fit very well with his observational results. Now, what about stellar winds? Well, okay, so like I mentioned before, I showed the impact of stellar winds on the cluster scale. So in the case of the Doradus, we see it can have a huge impact. And as these stars are forming, they're going to collapse down to the main sequence, or they're going to contract down to the main sequence very quickly. And as they contract, their surface temperature is going to increase. They're going to become more luminous, and their escape speeds are going to increase. And so these so massive stars at above 20 solar masses or above can drive these really strong winds. And then these winds will collide with the surrounding gas. You get the shock stellar wind material. And if you assume that all that kinetic energy from the winds themselves are thermalized, then you expect temperatures of millions of degrees Kelvin. And the hot gas pressure associated with this could potentially do a lot of havoc to the infalling gas. And so here I'm showing a similar simulation, but now we have turned on winds. This does not include magnetic fields. And we see that once winds turn on, so this is showing when the star is about 28 solar masses, you don't see a lot of impact from feedback from outflows or radiation right now, at least from this viewing angle. But once the winds, so at about 30 solar masses, the winds become stronger and stronger. And basically, you're going to generate this really hot, shock-heated gas that's going to find the path of least resistance. And so you can see here that this gas is traveling very, very fast, but it doesn't uncover. You don't have like a spherical bubble similar to what the simple picture shows. Instead, you kind of see that the hot gas is just going through the path of least resistance and filling these the cavities of where radiation pressure is causing these, is evacuating dense material. And so as you can see here, so winds turn on about here. When the star is at about 20 solar masses, that's when it becomes hot enough. And then as it continues to accrete material, it contracts down in the main sequence and gets hotter and hotter. The winds become stronger, and then eventually the winds become strong enough to shut down accretion onto the star. However, the picture kind of changes when you have magnetic fields. So now we're showing magnetic fields, so for similar masses, and we see that these hot bubbles driven by winds is less impactful. And then if you actually look at the accretion history of these stars, you see that once winds become important, you actually get a little bump in the accretion flow on the stars that eventually overturns. And so, yeah, at first it was a little perplexing because you would expect that that the wind feedback, just like in the non-magnetic case, should be really important, especially when the star is sufficiently massive. But again, we have the same effect like I showed with, with the confinement of the radiation pressure-driven bubbles. So here I'm showing a zoom in near the star for 4 different snapshots, and I'm just plotting the magnetic pressure divided by the thermal pressure. And you can see early on, especially when the star, you get this bump in the accretion flow, what's happening is that the magnetic pressure is so high, it's limiting the shock heating of these winds. You're still getting some heating, so that can actually, because we follow Bondi accretion, the accretion increases with higher temperature. And so you can actually, if you get this confining effect from magnetic tension, you can actually increase the accretion flow into the star. Eventually, the winds become strong enough that the magnetic pressure and tension cannot keep doing this, and so the accretion rate starts to taper off. So this is what we're seeing here is likely that for the highest mass stars, wind feedback, once the stars are massive enough, could be important at shutting off the accretion flow onto massive stars. So that was a nice theorist view or computational astrophysicist view of being able to look in as close as I want to see what's really going on and how these different feedback processes actually affect the formation of massive stars. And so the next little bit, I'm going to talk about some work from Grace Oliver, who's a grad student at OSU. And she did a multi-wavelength analysis looking at the different pressure components for compact H2 regions. So these are H2 regions that are less than half of a parsec in size and radius, and they encompass massive stars. And so these are massive protostars that are very young, that are still having a strong impact on their environment. And so here's an example. She looked at over 100 compact H2 regions, and here's just an example of a few in W49A. And so, like I said, she looked at a variety of different feedback processes. The first is the direct radiation pressure, and that depends on the bolometric luminosity from the star itself and the size of the H2 region. Likewise, she also looked at the photoionized warm gas pressure. So this is the warm gas that's produced by the fact that massive stars give off a lot of photoionizing radiation. The molecular neutral hydrogen, the neutral hydrogen is going to absorb that and then become ionized and heat up to about 10,000 degrees Kelvin. And then also using a large sample of infrared radiations and measuring the SED and fitting the SEDs for these H2 regions, he was able to also determine the pressure associated with the Desver-Prashas radiation. And then finally, using Chandra archival data and literally counting X-rays, which there weren't that many, she was able to infer what the hot gas pressure is from the shock-heated stellar winds. And the nice thing about this is similar to a lot of work by Laura Lopez, but on a much smaller scale, is that with this, for her large sample of H2 regions, she can see as a function of size, and so this can be a proxy for age or evolution, what feedback components dominate. And so what Grace found was that the infrared, the Desver-Prashas radiation pressure dominates early on, for most of her sample. The H2, so the warm gas pressure, is subdominant, very much so. And so she found that compact H2 regions are dominated, or the dynamics of them are controlled by the Desver-Prashas radiation pressure. And from her measurements, she was able to kind of get an estimate for what this trapping factor is. So this is for her whole sample. And she finds that the median value is a factor of 8. So this one, again, is from the direct, the first absorption of the radiation field, and that gives us our P direct. And then this trapping factor is our infrared, is from the infrared observations which gives us a proxy for the dust reprocessed radiation pressure. And so that's saying that the radiation pressure is enhanced by several times. And so this is why the dust is very important when considering the impact of radiation pressure on massive star formation. And then also one thing I want to mention too was these upside down arrows. This only encompasses, this is for the hot gas pressure measured, and these are all taking us upper limits. And that's just because, first of all, they required at least 10 counts of photons. They're literally counting photons. And then also, there's also source confusion. So the X-rays, so with Chandra, you measure from the 0.5 to 7 keV band, and the lower energy photons traces, this diffuse gas that we expect to see, this expanding gas. So you could get confusion if the gas is heavily confined or if it's from the star itself. And so this suggests that maybe we get these X-ray non-detections or source confusion due to the early confinement of stellar wind feedback that we're seeing in the simulations. Now, I'm just going to talk a little bit about, just go briefly into now going from these small scales down to the larger scales of star clusters, so evolved star clusters. And this is building off Laura's work. In 2011, she did this nice study on 30 Doradus, and my favorite H2 region. And she did a similar analysis looking at these different pressure components and found that that 30 Doradus is warm gas pressure dominated, but was probably dust reprocessed radiation pressure dominated early in its infancy. And so Laura also did a similar analysis for 32 H2 regions. So these are H2 regions, so giant or extended H2 regions that surround star clusters. And what she found was that they typically are warm gas pressure dominated, and that and so if we collect everything together, you find this transition, and this agrees with work from Mark Krumholtz and Matzner that kind of said that compact H2 regions for massive stars, if the luminosity is high enough, you become you're dominated by radiation pressure, and then you become warm gas dominated once you reach a critical radius. And so we're seeing this transition here. More work needs to be done to look at what's exactly happening for smaller H2 regions, but we do see this nice agreement with the theory that for massive stars, the dynamics of the gas that surrounds them early on is dominated by radiation pressure, and then switches over to being warm gas pressure dominated. Another thing too, from this work, especially with Laura's work on the effect of wind feedback from star clusters, is that what we find is that if you just look at the thermal energy in the hot gas, that the hot gas pressure is much lower than what you would expect if all the wind energy went into generating that hot gas and having that hot gas person surrounding the cold gas. And so this suggests that wind feedback in star clusters is not as efficient as one would expect. And that's assuming if all the wind kinetic energy is thermalized, which at first it should be, but then as this hot gas, expands, you can actually transfer the energy in a variety of ways. And so I won't go too much in the details. We did a full analysis looking at different ways you can transfer this energy. But recently, a nice paper came out from Lancaster et al. 2021 that showed that the classical picture of you just have a star in a uniform medium blowing a wind, that over predicts the hot gas pressure within the bubble, because the truth is that these star clusters are forming in turbulent environments. And so as the shock heated wind expands, it's actually going to mix with the turbulent material, the surrounding turbulent material. And if we look at the cooling function at the hot temperature that this hot gas is generated, the cooling function is very weak, so you get very efficient cooling. But if you mix, this surrounding turbulent gas, cold turbulent gas with this hot gas, you actually get gas that's like 10 to the 4, 10 to the 5 Kelvin that will then rapidly cool. And so with their new model, they're able to see compare and get realistic radii and shell expansion rates for the observed H2 regions around star clusters. And likewise, Monica Gallegos Garcia, she's a grad student at Northwestern. She was a Banneker student at Harvard for a couple of summers. She also looked at this effective wind feedback for star clusters. And she finds these really nice results too, where you do get this expansion from the shocking interstellar winds that grows, and it grows a bubble with time. But as these bubbles overlap, you get a lot of mixing. And that mixing leads to actually turbulence. So you actually drive subsonic turbulence because this gas, like I said, is really hot and really fast. So it's actually subsonic. But, and so it matches the subsonic Kolmogorov turbulence spectrum. But she also looked at here, so this is showing the cooling time divided by the expansion time of the shell. And you get mixing within the bubble itself. So it's not just the fact that you're developing instabilities between the hot gas and the surrounding cold gas shell. The fact that you can get cooling within the bubble. So even without turbulence, we find that we are losing energy due to driving this turbulence and mixing within this wind-driven bubble, and then also due to the expansion. And so I will just leave that there. So just to summarize, like I said, radiation pressure barrier is no longer a pressure barrier and is no longer a barrier massive star formation, as long as you have an optically thick accretion flow. And in our case, this is due to an optically thick accretion disk that forms around the star, and then also due to Rayleigh-Taylor instabilities, developing these Rayleigh-Taylor fingers that can fall down to the star. Then you overcome the radiation pressure barrier. Likewise, outflows are required. They're the main feedback component that really sets the star formation efficiency of star forming cores, and also the entry and outflow energetics of massive star forming cores. And then also in the context going from the formation of individual massive stars to the role of feedback in evolved star clusters is that around intermediate mass stars, the dynamics of the H2 regions is dominated or is dictated by radiation pressure. But once the bubble becomes large enough, or the H2 region becomes large enough, then warm gas pressure starts to dominate. And then likewise, the role of wind feedback from multiple stars leads to turbulent mixing. And then you can actually lead to cooler, more slowly expanding bubbles due to efficient radiative cooling in the star clusters, because this turbulent mixing will mix cold and hot gas that can cool very efficiently. Thank you.
All right. Thanks, everyone. Thank you, Anna, very much. So I see folks should just raise their hands. I see Shri already has his hand raised. So Shri.
Yeah, I had a couple of questions. On almost the second slide, you had the initial mass function percentage. I wanted to make sure I understood that right. It's a trivial point, but can you go back to that slide, please?
Oh, yeah. Yeah.
Yeah. So I didn't understand. If I understand, there's a Krupa 2001. It's a power law with a little break. And even at 10 to the -1 solar masses, mass fraction is 10 to the -1. Am I reading that right?
So this is this is normalized. Sorry, I made this years ago, and it's just taking the Krupa IMF, like the function that he gives. It turns over. So I think so. If you look at the Chabre IMF, so there's a few different IMF functions. I just use this as an illustrative purpose for the fact that massive stars are really rare. But the IMF turns over, I think, at lower masses.
So, but is it really saying that 90% of the stuff is below 10 to the -1 solar masses?
No, this is the normalized histogram. So if you integrate across this, then this is going through orders of magnitude. If you integrate across this,
So it
should add up to 1.
So it's not really the y-axis is not what it says. Fraction of stars with.
Yeah, sorry. So it's a probability distribution function.
Okay, I understand.
Yeah. So like if I had a real cluster of stars, I could assign numbers.
Yeah. Okay. Fine.
Yeah.
That's what. I was like, I thought there's a new theory here that I hadn't heard of. So.
No. Sorry for the confusion.
Yeah,
I will change that.
Okay. So then the question I had was, let's say I have two isolated accretion disks, same, disk which is the same mass.
Mm-hmm.
The center star is formed in both cases, and in one case the star is unmagnetized, or the material is unmagnetized and the star is unmagnetized. The other case, the star is heavily your whatever supercritical accretion disk. Everything is supercritical, m equals 2 or something. And you said something like in the second case, because you lose angular momentum due to magnetic fields, you accrete less. Could you explain? Give me a more understanding explanation.
Yeah. So so the magnetic pressure is going to slow down the collapse of the core itself. The magnetic torques are going to remove angular momentum from the infalling material. So that's why we get magnetic braking. That magnetic braking can be reduced if the field lines, so in the case of ideal RMHD, you assume the field lines are like glued to the gas. However, that's not necessarily true. You have non-ideal effects that can actually make the field lines less attached to the infalling gas. And the simulations I showed, they just include ideal MHD. So we get like very efficient magnetic braking, but we still develop an accretion disk. So I think the thing is that when you include magnetic field, you expect some angular momentum removal, and that will lead to so in the context of just circularization, with conservation of angular momentum, that for a particle gas that has a lot of angular momentum, it's going to be circularized farther away. But if you remove some of that angular momentum, then the material is going to fall closer to the star, and that's why we do achieve a much smaller disk at that point.
No, I don't understand that, because it's only a question of where you're setting your co-rotation radius. In the first case, unmagnetized, the co-rotation radius is set at the disk of the surface of the star. Okay. In the other case, it's the alpha radius. Fine. So why does that change the accreted amount? It changes the period of the star. In the end, the magnetized star will have a longer period, and the unmagnetized has a shorter period. But could you please explain why, in the two cases, the amount of material that is being accreted is different?
Oh, so you mean the magnetic field on the star?
No, I'm saying the magnetic field on the star is a consequence of magnetization in the gas itself.
Well, our stars don't have any magnetic. Yeah, the stars don't have any magnetic field. We're just finding the gas can be magnetized.
Yeah, but that gas magnetic field is not going to go away.
No. Yeah,
that's the reason your co-rotation radius is changing. When you put magnetic field, you're changing the co-rotation radius. What I am able to understand the change in period. They'll have two different periods. One is slow, other is fast. But I don't have a physical understanding why the accreted matter, the total amount of matter, will be different.
So the amount of material that falls to the star. So sorry, let me go to that figure. So it depends on the collapse of the core, right? So I think what happens is that as the cloud of gas is collapsing, you're increasing the magnetic field strength, because you're drawing in the field lines. So you're increasing the magnetic flux, and so that is going to beef up the magnetic field, which then is going to add a stronger magnetic pressure, which is going to slow down the collapse. And that's why you see that, early on, the accretion rate for both cases is similar, but then as the core is collapsing, the accretion rate actually drops them for the magnetic case. So the core, so eventually so in this case, at about a half of free fall time, the stellar mass growth is slower. And I think this is mostly due to magnetic pressure, to the accretion disk, because we don't have an accretion disk in the simulation throughout the full simulation. Does that answer your question?
Not sure. I need to understand this myself. Thank you.
Okay, I think it's more that the effect of magnetic field is that it just slows down the collapse of the core, and the massive cores tend to be much higher density, tend to be high density and have really fast free fall times. And so this is kind of adding an additional pressure component, slowing down the free fall time of the core. And that affects the accretion rate.
Oh, sorry. All right, I think Chris also had a question. Chris, do you want to unmute?
Hi, thank you for that amazing talk. I guess, can you make predictions on IMF variations, or including the IMS cutoff, with either metallicity or density? I know the rate limiting step may be the formation of star forming clouds, but not feedback. But I'm curious, since feedback can be driven by, either dust or lines, whether metallicity has a big impact.
I mean, I think this is directly related to what I'm working on with Phil and Mike Rudick and David Gushinov and others. So unfortunately, with my simulations that I presented here, the sample size is small. So the answer, and then also the setup is highly idealized, but I've been working with Phil and others, on this new StarForge framework, which is able to actually resolve the individual formation of stars, the formation of individual stars on the size scales that I'm doing with these Orion simulations. So this is really exciting, including all the relevant feedback effects. And so this is just like a sample simulation. Mike and David are running a bunch of simulations too. I'm looking at the more higher density clouds because I'm really interested in the formation of superstar clusters. And David and Mike are looking at the formation of like Milky Way-like clusters. And David just had a paper that came out recently showing, just not including radiation, but including jet feedback, and showing that when you include outflows from stars, that sets the low mass and the peak of the IMF, but you get a top heavy IMF, so too many massive stars. And so here's a sample simulation that I've been running with radiation, with jets and radiation. And so this again is showing the Krupa IMF with that cut off there. And so you see that once you include the relevant physics, you do match the IMF a lot better. I do still see a top heavy IMF, and I suspect that, based on the work I presented, that winds are probably going to be important at the top end. And so it's the radiation is going to be important here. And then once the star is massive enough for winds to actually, for strong winds to happen, that might set the upper cutoff of the IMF. In the context of metallicity, then it's going to be totally different, because in the context of metallicity, you could think of like the dust scales as metallicity. So high Z galaxies have less dust. So the dust for process radiation pressure is going to be way less important. Another thing too, winds are going to be less important because these are line driven winds. Well, if you have lower metallicity, then the winds will be weaker. So yeah, you're exactly that. And that's exactly what StarForge is looking at now. I mean, we do plan on looking at metallicity effects, yeah, hopefully in a few years, there'll be answers to that. And yeah, the nice thing with this new framework that Mike and David developed is, we can actually like have a large sample. My sample size of my simulations are small, but now, with Phil's Gizmo, with this Gizmo meshless method, we can achieve much higher resolution. So this is something that I've been working on recently. That's very exciting.
If I ask you to make a bet, sorry, I'm baking something. If I asked you to make a bet on low metallicity IMF, would it be top heavy or top light? Neither.
Yeah, to be honest, I mean, so 30 Doradus has a lower metallicity. I mean, it's an LMC. Mm-hmm. They find a top heavy IMF. To be honest, if winds are the ones setting, if winds are responsible for setting the mass cutoff for massive stars, then I would think more top heavy. And that if that's what we see, that would be really exciting, because that's what is believed to be observed in 30 Doradus. There's been a lot of debate with 30 Doradus, because I think when I started grad school in 2010, like people were like, oh, there's stars like 500 or 300 solar masses. And then a few years later, it's like, oh, there's 300 solar mass stars. Now it's 200 solar masses. You're really, one of the biggest problems is that in these star clusters, you get a lot of crowding. And so, yeah, I think I suspect that at low metallicity, you might expect more massive stars, but I think there might be other feedback effects that will become important.
Right. Thanks.
Yeah.
Thanks.
You're welcome.
All right, Ranga.
Well, there is evidence for a top-heavy IMF, at least at high redshift, based on the strength of the nebular emission, which is anomalously strong, even given the age of the stellar population. So the only way we can explain that is by having a top-heavy IMF at high redshift. But my question is there a mass limit to the high mass stars that you can form, or have you evaluated what the mass limit is in the current simulations, and how much wiggle room is there?
So in the simulations I showed, unfortunately, no. It comes to a point with those, because when you have radiative transfer, as I'm sure Phil can agree, you come to a point where you got to figure out what you want to do with your life. Like you can keep running them, or you can write the paper. I suspect, so unfortunately, like at the end of the first simulation I showed, we get to 60 solar masses, and that was at the time, the biggest that has been done in radiated or RHD simulation. So that was exciting. And then as I showed in the RAM pressure plot, the star could have kept accreting. So I suspect it's higher than that. But as we turn on more feedback mechanisms, then when you have outflows, you're losing mass to that. Lens can turn off. But I think with Star Forge, we're going to be able to answer that a lot better. And we're going to look at it, how it depends on environments and so on. So like I said, we're running these simulations for a variety of GMC initial conditions. I'm looking at the high mass end, at the much higher surface density where we expect superstar clusters to form. So that will be interesting to see if we get a top heavy IMF, because you might have such high RAM pressures that feedback becomes less important, and that will be important for kind of like high redshift galaxies in the sense of the very dense clumps, I believe, that have been observed. Yeah, so I think, to be honest, I think the results from Star Forge is going to kind of blow all these questions out of the water. Maybe I'm just biased, but we're looking at a lot of like interesting effects about how feedback affects the IMF, and what how these different components set the different mass scales. And so that's actively being worked on now. So I suspect there will be a lot of exciting papers over the next several years.
Okay, thanks.
You're welcome.
I had a very quick question. You showed the plot of only about a quarter, I think you said, of the injected momentum is effectively coupled to entrained material as compared to escaping.
Yeah.
Was that number significantly, or do you know, significantly different? Because I think your injected was radiation plus outflow. Did it differ substantially between the two components, or was that?
I only looked at that in the outflow simulations, the ones that included outflows, and
that was just for outflow, not for
that was
radiation.
just for outflows, yeah, because the radiation kind of impacts on smaller scales, and the outflow lobes don't align with the radiation pressure-driven bubbles.
I see. Okay, I just misunderstood. Sorry. Thank you.
Yeah.
Okay.
No worries.
Okay. Any other very quick questions? We're at about 10 minutes past the hour, so it's probably.
Oh God, sorry.
No. Thank you very